Today we will talk about continuous random variables. This is the third video in a four-part series. The main topic for today would be the gamma distribution. This distribution is useful when we're modeling events that are related to times. For example, component lifetimes or modeling waiting time distributions or the amount of time elapsed until something happens. To talk about the gamma distribution, we will first work through the definition of the gamma function, which takes input alpha, a positive number, and is defined as the following indefinite integral. The gamma function has some very interesting properties. For example, gamma of alpha plus 1 equals alpha times gamma alpha for values of alpha greater than 0. We can check that gamma 1 equals 1, and using induction, this lets us get gamma n equals n minus 1 factorial. So the gamma function is one function that, when restricted to the set of natural numbers, gives us the factorial function. The gamma function, when evaluated at half, gives us a square root of pi. This is a fact that we will be using at a later point when we relate the chi-square distribution with the normal distribution. For now, for values of alpha comma beta greater than 0, we let fx semicolon alpha beta to be defined as follows. And we note that fx is greater than or equal to 0 for all values of x, right? So all our exponents. And using the gamma function, we notice that the integral from minus infinity to infinity of fx equals 1. So this means that f is going to be a PDF of a continuous random variable. In fact, we will say that x has the gamma distribution with shape parameter alpha and scale parameter beta if the PDF of x is the function fx semicolon alpha comma beta. Note that when beta equals 1, we call the distribution the standard gamma distribution with shape parameter alpha. The PDF of the standard gamma distribution is defined as follows, which is obtained from the earlier formula by taking beta equals 1. Now, if x has the gamma distribution with parameters alpha and beta, then the expected value of x is going to be alpha times beta. The variance of x is alpha times beta squared, and the standard deviation is square root of alpha times beta. The CDF of x that has the gamma distribution with parameters alpha comma beta is defined using the following integral. Note that the CDF of x is the probability that x takes values less than or equal to x, and this is going to equal the CDF of the standard gamma distribution with parameter alpha evaluated at x over beta. So this calculation can be obtained by doing a simple change of variables, from going from the regular gamma distribution with parameters alpha comma beta to the standard gamma distribution. Finally, note that if t has the standard gamma distribution with shape parameter alpha, then x equals beta times t has the gamma distribution with shape parameter alpha and scale parameter beta. This is in line with noting that the beta parameter is actually scaling the standard gamma distribution with shape parameter alpha to give us the random variable x with shape parameter alpha and scale parameter beta. There are two special cases of the gamma distribution that we will be interested in. The first is the exponential distribution. This is obtained from the gamma distribution by taking the shape parameter alpha to equal 1 and the scale parameter to equal 1 over lambda. This will give us the exponential distribution with parameter lambda a positive number. The PDF of the exponential distribution is defined as follows, and the CDF is defined or calculated as 1 minus e to the minus lambda x when x is positive and 0 otherwise. Note that if x has exponential distribution with parameter lambda greater than 0, the expected value of x is going to be equal to 1 over lambda. The variance is going to be 1 over lambda squared, and the standard deviation will be 1 over lambda. An important application of the exponential distribution is when working with a Poisson process with rate alpha. In this case, the exponential distribution with lambda equals alpha will be the distribution that models the elapsed time between the occurrence of two successive events in the Poisson process, which can be things like looking for the arrivals at a bank or the number of hits that a website gets. If x has the exponential distribution with parameter lambda, we can consider the probability that x takes values that are greater than t plus t naught, given that x has taken values greater than t naught. Following through with this calculation, we note that the probability that x takes values greater than t plus t naught, given that x has already taken values greater than t naught, is exactly equal to the probability that x takes values bigger than t. To interpret this calculation, note that if x was modeling the lifetime of a component, then the probability that the component lasts an additional t units, given that it has already lasted t naught units, is exactly the same as the probability that the component would last t units without any additional information. This says that the distribution of the additional lifetime is exactly the same as the original distribution of the component lifetime. Another way of interpreting this is to say that the exponential distribution has the memoryless property. The next interesting distribution coming from the gamma family is the chi-squared distribution. And we say that the random variable x has the chi-squared distribution with parameter nu, which is called the degrees of freedom, if x has the gamma distribution with parameters alpha and beta, where alpha equals nu over 2 and beta equals 2. Putting these values of alpha and beta into the PDF for the gamma distribution with parameters alpha, comma beta, we get the following formula for the PDF of the chi-squared distribution with parameter nu. And the expected value of the chi-squared distribution can be calculated to be nu. The variance equals 2 times nu, and the standard deviation equals the square root of 2 times nu. The chi-squared distribution has many important applications. One in particular is its role in statistical inference for the population variance. Also, if x has the normal distribution with parameters mu and sigma squared, the square of the standardized variable x minus mu divided by sigma will have the chi-squared distribution with 1 degree of freedom. To summarize what we have done today, we spoke about the gamma family of distributions which have the shape parameter alpha and the scale parameter beta. We spoke about two special cases of the gamma distribution, the exponential distribution and the chi-squared distribution. This is all for now. Take care of yourselves, and I will see you around.